Okay, so recording now, and we're going to do the share. So I'm going to drop out of this chat thing. I'm going to do the share content. I'm going to share the application screen. And here we go. Boom. Okay, and I'm cautiously optimistic that this is working. So where we left off was talking about different RAM subtypes, right? So we had dynamic RAM, which was kind of the first generation of that kind of RAM. It was great for a while, but now it's old, obsolescent. There's synchronous RAM, which is all of the successors to dynamic RAM. Basically, it's the same kind of thing. It just works faster. And static RAM is a different kind of RAM that is bulkier. It physically takes up more space, but in very tiny quantities, it's blindingly fast. It's much, much faster than ordinary synchronous RAM. But the problem is, if it gets too big, right, you can't use large amounts of it because then the size of the RAM makes it slow because it takes the electrons a little while to travel around in there. Okay, so that's the thing. So static RAM, super fast in tiny quantities. Synchronous RAM, much faster than other types of storage like, say, hard drives. All right. So the next follow-up with this is something called RAID. RAID is redundant arrays of independent disks. Basically what that means is if you have a set of hard drives all in the same device housing. So the hard drives themselves, the hard disks themselves are physically independent, but there's one input-output interface. So the I/O there in the lecture slide, that is input-output. And the nice thing about it, it allows operation as a single logical unit. Now, there are different operation models that you can use to write data faster, right? If you're saving files to disk, that's writing. Reading them is, loading things from the disk. Or you can also improve reliability through making multiple copies of your data. Okay, so basically your different RAID models are all around how many drives can be read or written at the same time and how many copies of the data get stored and what forms of backup exist. So let's talk a little bit about that. The three basic techniques: striping, mirroring, and parity. Okay, so I'm going to drop out of this for a second. We're going to do a new share. We're going to fire up Paint here. Paint is very useful. And we are going to, this is strange. Okay, we'll stop that share. Good. Okay, now we got to start a new one. Working on this. We're going to try. There we go. Application screen. Come on. I don't know what the delay is here. Let me do the whiteboard, but it's reluctant to do the application screen. All right, we can live with the whiteboard. That's fine, I guess. So, your basic techniques. Let's see, I'm going to start here. Let's see. Okay, good. Striping, mirroring, and parity. All right. So, striping essentially means, this is a strange interface. I'm used to Paint, but Paint I like. Well, yes, the slides are posted up on Blackboard already. Okay, so striping is breaking file into pieces, and storing each piece on separate disks. Okay. This allows faster reads and writes because the disks can run in parallel. Okay, but also makes the system more vulnerable to failure. Okay, reason is, suppose you have three disks suppose you have, let's say, 4 disks in your RAID device. If you break up the file into 4 pieces, and put 1 piece on each, then what happens? Any disk failure will lose the file. Okay, so your system is going to be more fragile that way. It'll run faster, but it'll be more fragile to hardware failures. Okay. Next one, and change colors here. Let's do green. Mirroring is keeping multiple copies of each file in the RAID device. Okay, so that's basically, you're going to have multiple copies. Obviously, this increases reliability because you need to have multiple disk failures to lose a file. Okay, so striping will make it run faster, but your system is more fragile. Mirroring, since you're creating multiple copies of a disk, you have a backup. If something goes wrong with one, well, you still got the backup. Okay, the downside of mirroring, if the RAID device is fairly busy, like there's a backlog of reads or writes going on, then mirroring will make it worse. Okay, that's because anytime you write the file, you need to write to multiple copies, which adds extra work. Okay, so if your system isn't really busy, if somebody's only doing something with a file like once in a while, and most of the time your RAID device is sitting there idle, it's not a big deal. But once it starts to get busy, you're really going to feel that extra load from mirroring, because everything you want to do, if you've got to write 3 or 4 copies of a file, it's going to take 3 or 4 times as long. Okay, so it's much easier to get to that kind of backlog. The last one, parity. Okay, now parity is a very interesting concept if you haven't heard of it before. So the idea with parity is a way of providing error checking. Okay, if this were a CS course, we'd go into painful detail about parity. But this is not a CS course. This is IDS 200. Okay, so all we really need to understand here, parity is a way of providing error checking. So I'm going to give you an example. Suppose I have 3 pictures. Okay, well, suppose let's start, I have 2 pictures. And in one of those, let's do an ellipse, and we'll make it, I don't know, blue, I guess. Ta-da. Whoa, that's weird. Okay. And in one of them, the circle's up here, and the other circle's down here. If I only have 2 copies, of the data, and they differ, I can't know which is the original and correct version, right? If I only have 2 copies and that's all the information I have, and one of these things is not like the other, I have no way to tell that that's the original. Okay, but all is not lost. If I have 3 copies, draw another circle. If I have 3 copies, I'm going to try to draw it. Boy, this thing is not really going where I want it to. Whatever. Now, let's say those are the same. Okay? But if I have 3 copies, it's vanishingly unlikely that all 3 will have errors, that two of the three will have errors in the same data. So having a third copy makes it pretty easy to detect an error. Having a third copy makes it fairly easy to recognize errors. And that's essentially what parity does. Parity is a way of keeping information about the data so that you essentially have 3 versions of the data. And then if something goes wrong, you can not only recognize there's an error, you can recognize what the error is and fix it. Okay, but as with all things, there is a price. Parity with mirroring will really slow down system write actions, because any change to one file necessitates changes to all files to keep up with the parity scheme. Okay, not only to a little part of it, but throughout the entire file. Basically, you need to recopy big chunks of it. So with mirroring, yeah, if you change something, you can change that little piece of it sometimes. But with parity, the changes tend to be much more significant. Okay, so we're going to take a pause here for a second. I'm going to turn off this sharing. Boom. Okay. So how are we doing? We got the chat here. Let's see. Okay. I hope that makes sense. That's the core stuff of RAID. Okay, so again, what you need to know about this, what RAID is, and then the issues of the 3 basic RAID techniques: striping, mirroring, and parity. Okay, so I explained what they are. Really, you need to know what they are and what they're for. You don't have to provide detailed explanations of why parity does what it does. But if you're interested, you can, certainly look that up if you're an IDS person. Okay, well, I'm going to return us to the slides. Oh, good. Somebody has a question about last lecture. Sure, go for it. What you got? Solid state drive. It's basically a faster of a mechanical hard drive. Most machines you buy these days have solid state drives instead of hard drives, instead of mechanical hard drives. Yep. Okay. Oh, it'll all get posted. Don't worry. RAID is a bunch. It will all be in the lecture. Okay, but sure, I'll go ahead and post it. I'll go ahead. I'll make it briefly visible here. There's really some strangeness. Oh, there we go. No, there's some strangeness with this. That stuff has disappeared. I'm still figuring out what else going on here. All right. Sometimes the sharing works well, and sometimes it does not work so well. All right. Yeah, you got to know the stuff, but don't panic. I mean, the exams are going to be open book, so. All right, we'll come back to that. What did I skip? Non-volatile memory slide. Oh, yeah, sort of. That's the stuff we talked about before. So your 2 kinds of non-volatile memory, that means it's permanent. It doesn't go away regardless. Okay, so a couple of them. So read-only memory, ROM, is like chips or DVDs or CDs. And the other kind is flash ROM. So NVRAM, non-volatile RAM. Okay, and of course, things like hard drives as well are also non-volatile memory. So anything that doesn't go away when the memory doesn't go away when the power is lost, that's non-volatile memory. Okay. All right then. So let's we'll move on. I'm going to try to yeah, here we go. Now I have it back. This is strange. Okay. I got PowerPoint again. Okay. So the next slide right after RAID, hard drive speed. Okay? So this applies to a point to solid state drives, which although they're faster than ordinary hard drives, they're much slower than regular RAM. So for hard drive speed, basically you have a disk that spins around like an old-timey record player. Okay, and because there's that kind of physical delay, because there's something physical moving around in there, basically the disk has to move to the right spot underneath the drive head. There's always going to be a few milliseconds delay anytime you try to access a new point. If you can have a sequential string of operations, like reading all the data from one track, just like you're playing one song continuously on a record, it's going to go a lot smoother. But still, it's going to take more time than RAM does. Okay, so rough numbers, hard drives are about 100 times cheaper than RAM. So a 1 terabyte hard drive, you might pay like $50 for that. 8 gigs of RAM, though, you might pay about $40 for that. So you have a whole lot more capacity in a hard drive. 1 terabyte is about 1,000 gigs. The downside, of course, is that hard drives are much slower than the same amount of RAM, and that makes it too slow for many real-time applications. For example, suppose you have a video game you're playing. Suppose you're playing Angry Birds, right? And you move around the slingshot and you got the bird flying through the air. When every action of that takes many reads and writes from RAM, going to happen super fast if it's in RAM, right? It can basically play out at real time. But if for every pixel you had to call the hard drive and find the thing and figure out where to put it, then it would be super slow, right? If basically every one of those actions took a few milliseconds, collectively they would add up to make the game go incredibly slowly. It'd be very frustrating. So RAM is great for when you need speed, which you do in most applications. Hard drive is good. Hard drives or solid state drives or other storage are much better for that. They're slower, but for the right application, they're fast enough, right? So if, for example, you're loading up an Excel file, you only have to do that once, right? You pull up the file, there you have it. And then the work that you're doing, you do in RAM. Okay, same thing applies to Facebook, right? So in Facebook and a number of other large-scale systems, they often use some version of what's called an in-memory grid, right? So the grid is a very large bank of RAM, so that can be super fast, and it's typically supported by a large group of hard drives. I'm gonna bring up Paint here. We're gonna stop this share, and I'm gonna bring up Paint. Let's see here. There we go. Okay, so I hope you can all see that. Can you all see Paint? It's not really cooperating. No. Yeah, it doesn't want to let me use Paint. This is so bogus. Thank you. Thank you for your stuff. I guess I'll use the whiteboard, even though the whiteboard kind of sucks. All right. So the idea with these systems, there we go. Now I actually see some stuff. Weird. Okay. So I have RAM at one point, and I have hard drives at another point, right? And remember, RAM is fast, but expensive. Hard drives, slow, but cheap. Okay, that's the overriding thing. So what you'll typically see, you'll have the RAM part and the hard drives. And so I'm going to draw some arrows going back and forth. Da, 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 da. Okay, and here's a query coming in. Okay, so anytime you're retrieving something, let's say, suppose you're retrieving some data, like a photo, on Facebook. Okay. First, you're going to check in with RAM, and you're going to say, hey, is this thing stored in RAM? Okay. So first, check RAM. If it's not there, if not present, right, then it's in the hard drives. So you go there. And periodically, you do backups. Okay, so everything in RAM needs to be backed up on hard drives so that a power outage doesn't lose everything. Okay, that's the basic idea. Okay, and the other thing, periodically, you'll update what's stored in RAM typically based on popularity. Okay, so if some data is very popular, right, like there's some breaking news story that everybody wants to see, you're going to store that in RAM, so it's easy to retrieve by a million users. On the other hand, at the end of the day, right, breaking news is now broke news, and so it's not going to have that many people tracking that particular article, so it gets pushed off to the hard drive. You'll still keep it, but you don't need to have super fast immediate access to everything. So that's the point of this kind of in-memory grid. For the very popular common requests, you store them in RAM so that you can respond very quickly to them. For the other stuff that don't get as much traffic, you can keep those on hard drives. And periodically, you have to do some churn between what's stored in RAM and what's stored on hard drives, and you need to periodically back up what's in RAM so that you can actually keep it permanently. Okay. So good. I'm going to bounce back to the slides then. Okay, so that's what an in-memory grid is, right? For very popular requests, you can operate at electronic speeds instead of physical speeds. Okay. This brings us to our concept of caching, which we talked about the other day. So caching is a widely used principle in information technology, and it just means keeping the stuff you use a lot where it's easy to read. So hot data is data that's used often or recently. Cold data is something that hasn't been used often or recently. And it's applied in a lot of different ways. For example, where certain web pages are stored on servers or where the data for applications is stored on servers. There's going to be some parts of the memory that run faster, some parts that do, right? Or some parts of storage that's easier to get to. That's where you put the stuff. For example, if you're trying to find a particular web page, one of the things you typically have to do is scan down a long list of page entries to find out where that web page is located. Well, if it's a very popular page, you can put it at the start of the list, right? And then you don't have to scan through that entire list to find that very popular web page. Other stuff, database tables. If you have a large database system and certain information in that is used much more than others, same thing. You put those database tables in a part of memory or part of your system that works faster. Okay. As a practical example, Facebook photos from 5 years ago, right? I know we got this thing now where Facebook will resurrect old photos of yours from X years ago, but in general, you don't go through and dig through your Facebook photos, the old ones, too much, right? It's all about what's now or what's last week, but 5 years ago, most people aren't going to look at them that much. So those get put more or less in cold data, right? But things that are from the last couple days, those are probably hot data. Okay, so an example of this, hybrid, right? So this is Oracle's in-memory database cache. Same kind of system I was talking about a little while ago. So it's a hybrid system with RAM and hard drives, which is designed to balance cost and speed. Again, RAM is fast but expensive. Hard drives are slow but cheap. Okay, and the issue here, the reason why this works, for most organizations, most of their data is going to be historic. It's going to be rarely used. So it's not that important to deliver it up quickly. And you can actually see this on Facebook, right? If you want to dig through your whole Facebook history, right? When you go to Facebook and you see all of your old, you can look in at your profile and see all the things you've posted over a few years. the further you scan to the system, the longer it takes to find anything, right? So if you're looking at stuff within, the last month, 6 months, all that's going to come up pretty fast. But when you start getting back to like a couple of years or 3, 4, 5 years ago, you'll see it goes real slow because every one of those things Facebook has to pull out from someplace that they're like, oh man, I can't believe you're asking for this stuff. We had it packed away in the garage somewhere. Okay, so rarely used, again, stored on hard drives or otherwise less accessible, frequently used or more recent data stored in RAM for fast access. Okay, and you need to do backups. You might do them synchronously so that anytime something happens in RAM, you pretty quickly change that in the hard drives, or you might do it asynchronously. You might say do a batch at the end of the hour or the end of the day to make sure that everything in RAM is synced up with what's on the hard drives. Okay, but this is just an example. Don't specifically need to know about Oracle system. Okay, another issue, replication. Okay, so Facebook stores multiple copies of data, right? So the question is, where and how is all of this going to be stored? So suppose your organization runs 10,000 or so servers for application users all over the world, like Facebook. Well, basic question, should they be centralized or not? Well, what happens? So if all the data is stored in one massive centralized location, what happens? Well, first of all, there's going to be a certain amount of distance delay. Okay, so anytime these messages are traveling over networks, it's going to take a little time because the electrons don't instantly teleport. And typically the time is about 1 millisecond per 100 miles. So if you're talking about a data center on the other side of the world, ballpark number about 1/10 of a second delay. Another thing, traffic spikes, when they happen, they're going to affect all the users, right? So if there's some big burst activity, then everybody's going to feel it. Another issue is it's difficult to optimize availability for all users. Example, I'm going to pop out of this for a second. Okay, so I'm going to share the whiteboard now. Here we are. Okay. So basic problem, suppose I have users from all over the world using my data center. And I hope that works right because I got some window here blocking it. Sure. Okay. So what's the next issue? Well, those users will very likely have different interests. Okay, so for example, if it's daytime hours for the US, right, there will be a lot of requests for US specific data. On the other hand, right, if it's daytime hours for Europe, there will be different requests. Okay? So the problem becomes when you try to cache what's relevant, you have a constant flipping back and forth, right? So at the US daytime, then you flip all the US stuff becomes relevant and you have to cache that. European daytime, then you flip back to them. So there's a lot of issues with that. But if each data center is fairly localized and covers a small-ish part of the world, the user's interests will be much more homogeneous, right? The same. So you'll have more, more people in the system at 4 p.m. than at 4 a.m., but their interests will still be similar. Okay, so that's one of the issues there. So for all these reasons that are discussed in the slides, I'm going to bounce it back to PowerPoint then. For all these reasons that are listed here in the slides, you generally want to have multiple data centers covering specific parts of the world rather than have one massive data center that serves all worldwide traffic. Okay, so what I just talked about there was why optimizing availability is less effective. The other thing is it's not gonna be as easy to like shut down a big part of your system at say 4 a.m., right? If it's 4 a.m. in the US and it's a US data center, then yeah, you can, shut down a large part of that or do other things in the back. You can synchronize databases. But otherwise, right, if you have a fairly constant load, then you have to manage around that. The last thing, potentially brittle reaction to failures, right? So if one data center goes down for some reason, there's an earthquake, there's a fire, whatever, you can direct part of that load to other nearby data centers and, have your system still be up and running. But if your one and only data center is in California and that big earthquake hits like we've been hearing it's going to for the last 100 years, well, then yeah, there pretty much goes your whole operation. Okay, so the solution to this issue is decentralization. And essentially what Facebook and a lot of other organizations do, they store multiple copies of data at separate server groups worldwide, right? So they'll have a data center, say, for the West Coast, for the Central US, for the East Coast, one in London, one in Tokyo, one in Europe somewhere, one in South America, one in Africa, maybe a couple in India, I don't know. Okay, so they'll have data centers all over the world. And when necessary, requests for data that are not available locally can be sent to other server groups, right? So for example, obviously I've been in the United States for quite some time. Most of my Facebook friends are also in the United States, but not all of them, and some of them might be traveling to other countries. So if I post a picture from some recent vacation of mine, it'll immediately get uploaded to the Chicago area data center, right? And it'll be echoed out to my friends in other places. Now, suppose one of my friends who lives in Chicago is traveling on the other side of the world. Well, that data center is probably not going to immediately have my picture because Facebook is not going to expect that there's going to be a big interest in that picture. Instead, if my friend on the other side of the world asks for it, what'll happen first is Facebook will forward that request from their local area to the Chicago data center where that picture is actually stored and send it to him. But if there's a whole cluster of requests from the other side of the world for some, suppose I post up some video and it goes viral for whatever reason, and they're getting all sorts of requests from all around the world, if it gets popular enough, that video might actually be stored at data centers all around the world. Okay, so that's the idea. Number one, if you're decentralized, you're giving people what they need where they need it. So there's less latency because latency means basically how long it takes to get a response to your request. Well, if the users are physically close to the data center, there's going to be less delay from travel time. Other things, you can prioritize locally useful information. For example, in Tokyo, most of the articles would surely be in Japanese, whereas in the United States, most of the articles would be in English. And you can fairly well allocate them that way over data centers. Okay. So that's why they do that. Now, specifics to Facebook. So friendships and activity are pretty solidly correlated with geographic proximity, right? We tend to be friends with people that we're physically close to, right? So that's especially true in high school. You start making friends, they're in your city, you go to the same high school, you're friends with them. To an extent, it happens in college. Then there's a little window where it all kind of blows up because all your friends go to different colleges all over the world, and you're still friends on Facebook. And then it tends to come back to an extent later on. But there's definitely a positive correlation. It's just not a perfect correlation. Anyway, so Facebook, they want to keep information relevant. So if I post a picture of something, then people are going to assume, well, most of your friends are in Chicago, therefore that's where Facebook is going to initially store that. But if other requests come in from around the world, then yeah, Facebook might replicate that picture to other data centers. Okay, so now we're getting into the key stuff about Haystack. All right, so Haystack is Facebook's system for storing photos. Now, if we look at this chart, if you look closely at this chart, there's a couple things, but I'm gonna draw it over in the whiteboard so you can see a little better. There we go. Okay, and the curve basically looks like this. So it's a cumulative distribution, okay, over time. So down here, we'll say like 1 day, and then 1 year, 2 years, and so on. And the graph that's in the slides is several years old, so it's changed, but the idea is fundamentally this. Something like 40% of things on Facebook that people are looking at, pictures that people are looking on Facebook, are within the last few days, okay? But something like 80% are within the last year, which means for Facebook, and then, you know, if we go out farther enough, we get to that 100% here. Which means the key takeaway from this, even though recent photos are much more popular, okay, the old photos are popular enough that Facebook doesn't just put them in super cold storage, right? Because it knows people do occasionally ask for them. So that's the fundamental issue. Okay, and when you have as many users and as many photos as Facebook has, keeping that many up to, you know, available is a big issue. So the key thing here, way too many photos to store in RAM. Okay, even this 80% here, if Facebook could perfectly predict it, that would be way too expensive to store in RAM, and it would still have some people that are unhappy because these old photos are a problem. So what did Facebook do? Well, let's see if I can and blank that out again. Okay, so circa two, Facebook solution was to outsource a lot of the issue. Okay, basically they contracted with a content delivery network, or CDN service, to deliver the most popular data quickly. Okay, so think that kind of hybrid RAM and hard drive system that we were talking about earlier. But the problem is the service was expensive and requirements growing very quickly. Okay, many photos. Okay, so basically it was unsustainable. At projected growth rates, Facebook would not be able to maintain photo delivery speed. Okay, that was going to be a big problem, right? Because there was too much traffic to pay this content delivery network to do it for Facebook, and putting it all on RAM was going to be way too expensive. So they were going to have to shift to kind of slow hard drives. It was going to be a problem. So what was their solution? Well, first we'll talk about the situation. So the situation is this. When a user pulled an image from Facebook, a few things happened. Okay, first, the user had to retrieve the image metadata. So things like permission levels. See if the user was even able to see it. Okay? And that happens from one hard drive. Then the photo itself had to be looked up in the system, right, to find it. That entails another call to a hard drive. Then, finally, Facebook actually retrieves the photo. But different photos would often be stored, let's say, carelessly. Will often be stored non-sequentially. That's the best way to put it. Okay, so they weren't right next to each other on the hard drive. So all of this, the multiple hard drive requests and the, non-sequential photos really slowed the system down. Okay? So anytime, if you were doing in RAM, if you were looking up these lists in RAM, it could be really fast. But if you're going to hard drives for each one of these things is going to take several milliseconds to find what they're looking for. And over the course of the day at Facebook's volume, those delays really add up. So the solution was Haystack. Okay, and the key innovation was keep the image file, metadata, and location in the URL. Okay? So the URL, Uniform Resource Locator, is basically the web address of the image. Okay? So anytime somebody tried to pull something from Facebook under Haystack, instead of having to do multiple calls to the hard drive, basically, when you click on the image, right, on the image thumbnail, you already have all the data you need to find the image. Okay, so it's much faster. The other innovation, important but lesser, the other innovation, grouping photos together in albums. Okay, so they could be retrieved sequentially and faster. Okay, so just like if you're doing something on a hard drive and you can just read all that data in one continuous stream, it's going to be a whole lot faster than if you're bouncing around all over the surface of the hard drive grabbing what you can. So the net outcome, basically overnight, Haystack tripled Facebook's photo delivery capacity. Okay, that's huge. That meant, number one, it gave them a lot more freedom to put more popular data in their own system, right? Because they could deliver stuff faster, so they didn't have to rely on the content delivery network as much. And then, again, they didn't have to do massive investments in hardware for a little while. So basically, reduced reliance on CDN, able to push off some major hardware upgrades, major and expensive hardware upgrades. Okay, and I'll add kept Facebook fast and viable. They were still making money. Okay, so that's the key takeaway from Haystack. Basically, by doing a smarter job of how they were arranging their data and how they were accessing it, they massively increased their system capacity and were able to save lots and lots of money. Okay. So let's stop this for a second. I'm going to stop sharing. Okay, we have some chats here. We got nothing. Okay, we haven't had anything in a little while. That's good. Okay, good. Okay, So I'm going to move on a little bit. We'll resume a little bit more with the slides. We're going to do this. We're going to go back to our PowerPoint, and I'll allow some time at the end. We'll ask for asking some questions. Okay, so here we'll go through the Facebook stuff. So Haystack, again, this is the chart that I talked about. Some links to articles about Haystack if you're interested in those. The one that's probably the easiest to read is the first one under the conference presentation. So it says usenix.org, legacy, blah, 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 beaver.pdf. That's the one that talks about the system. And again, even if you're not an expert in this stuff, there's pictures and you can understand it pretty well. Okay. So this is a system, object storage. Of databases, you build into the structure of the database itself what kind of data it's going to store. So for example, if you have a database table that's a set of customers, you know every customer is going to have a first name, a last name, an address, an email, a phone number, and you set up the table to require that every customer has those things. That's typically how you would set up what's called a relational database. Object storage is a little different. It tends to be you store lumps of data, which could have widely varying attributes. So while a customer would definitely have, you know, name and address, phone number, email, all that, and object storage, you could have it be whatever you want. You could have one object be an image, another object be a list of customers, another object be, I don't know, a text document of some kind. Every object could potentially be different. The advantage of object storage in general, you can pack the data in tighter because you're not bound to that particular framework. For example, if you say you're going to allow 20 bytes for a person's last name, that's going to be true whether you use all 20 or not. So what can happen is you can have a lot of basically dead space in your table. But with object storage, you don't have to do that. You maintain a list of what all objects are there, and then you just add them in one after the other. So it tends to be a much more efficient use of space. And when we talk about Facebook's system that, you know, is approximately 1 million hard drives worth of data, yeah, that sort of efficient space usage becomes pretty important. Okay, we'll talk more about that eventually, though. So the main point from Haystack, fewer output operations, seeks, that's where the hard drive, the drive head is trying to seek whatever new point on the disk it has to find. So if there are less seeks, then everything is going to go a lot faster. So it puts metadata in memory, not on disk, stores photos together in groups, and users they upload those photos as groups as well, so they get rich that way. So all that together, the system worked much faster, especially for the long tail of older photos. And there we go. Okay. So I'm going to very briefly introduce the concept of databases, and then I'll allot some time for questions. So database management system is basically a system for storing data, but not just storing data, being able to retrieve it quickly as well. So the sort of things you might keep, for example, a particular photo, or the set of users who have liked a particular photo, or all photos posted by a particular user over the last 2 weeks. And Facebook, in some sense, uses all those, right? You go to Facebook, you can retrieve a particular photo. You can look for yourself. If you look at a particular photo, right there is going to be the list of all the people who have liked it. And if you look at a particular user's profile, right, when you look at their profile, you'll see some string of recent activity, which could very easily include all of their activity for your prior 2 weeks. Okay, so there's two main approaches to databases, relational and NoSQL. So relational, RDBMS, Relational Database Management System, that's what we'll talk about most in this course. It's certainly what we'll be doing in Access, but NoSQL is important too. And within the last few years, it's become a big thing to have sort of intermediate database styles between the two. For example, Google uses one called NewSQL. That's sort of an intermediate stretch between the two. Okay, so the basic idea with relational databases is that data is stored in a hierarchical way. So you have tables, rows, and columns. The table is a set of records of a particular type. For example, a list of photos or a list of Facebook users. Each row or record is a particular thing of whatever the table's type is, right? Like a specific photo or a specific user. And the columns are the attributes stored corresponding to each record in a table. For example, for photos, you might keep track of their size, their location, where they're stored in your system, and who the original user was that posted the photo. On the other hand, for users, you might track information like their name, their password, their profile picture. Now, each table is composed of rows. Each row in a table contains the same set of columns. That's the basic structure of a relational database system. Okay, so I'm going to do one more slide, and here's an example. So this is a list of customers. So we start off with Albert Anderson. He's got an email, he's got a password, he's got a birthday, ... He's got some other fields, and he's got some system address for his profile picture. And Betty Barilla, Charlie Chupacabra, other users, they all have the same information. But down at the very end, Zachary Zug, again, got the same stuff. Okay, so in a relational database, you have a table. Every entry in that table is going to be the same type of thing. So this is a table of, let's say it's a table of system users. So every one of those records, every one of those rows is a system user, and every one of those system users has the same set of information, right? They each have an email, a name, a password, a birthday, and profile picture. Okay, that's the basic structure of relational databases. We'll come back to that. We'll wrap up this lecture on Thursday, and we'll start in on the next Facebook one. So, all right, so let me ask, does anyone have any questions about any of this stuff? I know we covered a lot of material today, but any questions? Now is the time for questions. Hello. No TAs yet for, oh yeah, if you want to talk about that. We're having a meeting tomorrow. I'm going to stop the recording then.